In this video, we are going to see how to manipulate the registers to obtain the required PWM, which is necessary for controlling DC-DC converters. So first of all, we should understand what are the timers which are present inside Arduino. There are three timers, 0, 1 and 2, out of which 0 and 2 are 8-bit timers, and timer 1 is a 16-bit timer. So what do we mean by 8-bit or 16-bit? In 8-bit timers, the counter register, which will get incremented every time whenever a clock signal comes inside it, will be of width 8 bits. So it can go from this value, that is 8 zeros, to 8 ones. So this will obviously give you how many states? 2 power 8 states basically. And if you take a 16-bit timer, its width is 16-bit. Its counter register width is 16 bits. So it can count from 16 zeros to 16 ones. So it has 2 power 16 states, 2 power 16 values, count values. So this is how it is. So whenever we say a 8-bit counter, we not only just mean that the counter width is 8-bit, but also the corresponding compare registers value, compare registers width also as 8-bit, because the content of this is obviously going to be compared with the content of this. Similarly, the content of this will be compared with the content of this. Obviously, they have to be of the same size. So this is how the timers of Arduino are designed. And as an extra point, we have 6 PWM pins. You can see 2 here, 2 here, and 2 here. 2 pins are connected to each timer. Please do not confuse that this register and this pin are related. No way. It's nowhere related. It is just that 2 PWM pins are available associated with each timer. For each timer, whenever I say a timer, it constitutes of all these important registers. So each pin is associated with, 2 pins are associated with each timer. So we are going to focus only on 16-bit timer in our discussion. And so 16-bit timer is connected to OC1A pin and OC1B pin. Now what is OC1A and OC1B? OC1A and B are merely just pins which are available on your Arduino board. Now OC1A is pin 9 and OC1B is pin 10. So we have OC1A and B, that is pin number 9, which is here, and pin number 10, which is here. If you want to zoom it, you can zoom a little bit. You can see here pin 9 and pin 10. These are the pins from which I will take my PWM. Obviously, when you are connecting two wires, if you are trying to take output out of pin 10, for example, you have to connect a wire between pin 10 and any ground, either this ground or this ground or this ground, any ground. So you'll take 2 wires. So you'll get the PWM across this. Now the discussion is how to get the PWM. So here we can see that there are registers associated with this. If you are not very confident on the basics of production of a sawtooth waveform or how a PWM is produced, the basics of it, I've already put a video, the video just before this video in the playlist. I recommend you to watch it if you are not very strong on the fundamentals. However, if you are strong on the fundamentals, we can proceed further. Now we are going to first talk about this register, TCCR1A and TCCR1B. So these two are 2 8-bit registers, right? So this is the register. Here we can see that there are some bits which will control. So what does this TCCR register basically do? What is this used for? It is used to instruct your timer to operate in a particular way. Use OCR1A for this purpose. use OCR1B for this purpose, count up to this value. When it reaches this value, come back again. All these are sets of instructions which we want the timer to obey. So we will give those instructions by configuring the bits of this register. So that's what this basically is. First, we will see. So you can just on an overview, you can see these 4 bits form a family together. We can study them together, and then this WGM bits, which are split across these 2 registers, we'll see together, and the clock prescaling bits we'll see together. Right. So first, let's talk about WGM bits. So this table gives you. This is taken from the data sheet of Atmega 328P. This table gives you the various ways in which you can operate your timer. If you are interested, you can go through all the ways. To just focus on the point of controlling a DC-DC converter using Arduino, I will directly tell you which mode we are going to use here. So first, what does WGM stand for? WGM stands for waveform generation mode. What is the waveform which we want to generate? Basically, there are 2 waveforms which are used for producing PWM. One is a triangular wave, another is a sawtooth wave. Using either of these 2 waves, you can produce PWM. Now, this triangular wave production is something like this. If this is your x-axis, you start from here, go up, come down, something like this. And the sawtooth production is something like this. Go up, it will be in the form of ramps. Now this, in Arduino terminology, it's called phase correct PWM. This, in Arduino terminology, is called fast PWM. So this is just a terminology, whether you want to produce a sawtooth wave or whether you want to produce a triangular wave. Now we want a sawtooth wave, so we are going to choose this particular configuration, which is the last configuration. What does the last configuration say? The last configuration tells you that if you write 1 in all these bits, that is, if you write 1 in all these bits, then it functions this way. How does it function? It will be in fast PWM mode, that is, it will produce a sawtooth for you. Point number 1, that's clear. Where does it stop counting? Your counter register is here, it's called TCNT, and it will keep incrementing with every clock pulse. So what is the top value? So up to what value does this count? What is this value? That is decided by your OCR1A register. Whatever number you are storing in your OCR1A register will determine up to what value you should count. For example, you want to count every 800 clock pulses. So what will you do? You will put binary of 800. You will convert this decimal number of 800 into binary. This may be some 0 something. This binary of 800 you will load into this OCR1A register and keep it. So the moment this counter keeps incrementing 0 to 1, then 1 to 2, and 2 to 3, and so on, after it reaches the binary value of 800, it will fall down. It will reset itself. So OCR1A determines up to what value it will count. Now, what is the place at which my registers get updated? Now, assume that in my program, I am suddenly changing this value of 800 to suddenly 1600. For example, if I am changing so, it should get updated. But while it is counting like this, it's counting and again resetting. It's counting up and again resetting. While this process is happening, and if I'm updating the value somewhere here, where will it be reflected, or when will it be reflected? It will be reflected only at the next time when this is reset to 0. That's what he's saying, that update of OCR1 value at bottom. So whenever it reaches bottom, only then you update this value. This is what he's trying to tell. Next, it's called timer overflow one flag. So when do you want to set this particular flag on? There's another flag available in another register. Let's not focus so deep into that. This flag is set that it goes to 1 when top is reached, when OCR1A is reached. So here top means you have to trace it here, and here it is OCR1A. So when OCR1A reaches, it will set its overflow flag on. Now, this is about the WGM bits of this register. Moving on, we have several ways to produce PWM. If this is my sawtooth, if this is my sawtooth, and if this is my duty ratio, I can produce pulse with a logic, or I can write a logic which says something like this. Whenever my duty ratio is dominant, whenever it is higher than the sawtooth, give me a high pulse. Whenever the duty ratio is less than the sawtooth, give me a low pulse. Whenever again it's high, give me a high pulse. So this is one logic of producing PWM. There is a logic contrary to this. I can write my logic in such a way that whenever my sawtooth value is more than the duty ratio, give me 1, otherwise give me 0. Give me 1. Here it is less, sawtooth value is less, so it will give me 0. Here sawtooth value is more, it will give me 1. I can produce a PWM like this also. Either way is possible. So which way do you want to produce? So I want to produce it this way. So for that, you need to instruct that to your timer. I want you keep your counter value here. This is basically the content of your counter register. Keep incrementing it. The moment it reaches your OCR1A, stop it. Again, reset it to 0. Keep counting. And this value is stored in OCR1B. This duty ratio value is stored in OCR1B. Now, whenever this is happening, whenever this particular match, otherwise called as a compare match, is happening, at that time, in the PWM pin, take the PWM pin and write 0. Again, when this kind of overflow is happening, when this kind of reset is happening, in the PWM pin, this is a PWM pin 10, write this to logic 1. Again, when this compare match happens, take the PWM pin, that is the 10th pin, write it to 0. So this is the way in which I want to produce my PWM. I want to instruct this to my Arduino. So that is done by setting your COM1 A1 and COM1 A0 bits, or COM1 B1 and COM1 B0 bits. What does this say? It says that I want to produce my PWM in non-inverting mode. What is non-inverting mode? If you read this, you will come to understand. I do not wish to read this again. If you read this, you will come to understand that it is the same thing. So I want to produce my PWM in non-inverting mode, so which is this instruction. I want to make it obey this. So I will put my A1 or B1, whichever, as 1 and 0th pin as 0. So what does this COM1 A1 and COM1 A0 and what does COM1 B1 and COM1 B0 stand for? See, this one, the first one, COM1, that one stands for first timer 1. It stands for timer 1. This A1 bit and A0 bit stands for bit number. So when we say A, what does A mean here? A means that it is OC1A pin, which is pin number 9. If it is B, then it is related to OC1B pin, which is pin number 10. Now I am going to obtain my PWM out of pin number 10. So I will write 1 in this register and 0 in this register. That's what I'm going to do. So this concludes the story of COM bits or compare bits. Now we have these three left. My Arduino system clock frequency is 16 megahertz. I can either operate it in 16 megahertz, or I can operate it in 16 by 8 megahertz. That's what she's telling here. Clock input output by 8, or I can operate it in 16 by 16 megahertz by 64, and so on. So which frequency do I want to operate my clock? It is always better if my clock frequency is as high as possible for better resolution and other purposes. So I don't want any pre-scaling to happen. That is the reason why I'm choosing no pre-scaling value. So this bit will be 0, 0, and 1. So I want no pre-scaling to happen here. I want to retain my 16 megahertz as it is. Now these are the contents which should be present in the register if I want to obtain the desired PWM for my Arduino for controlling a DC-DC converter. I have put on all the values here. So this is how it looks like. All the WGM bits are 1, clock pre-scaling value is 1, meaning that no pre-scaling. Then all these are 0. I am not using 9th pin, I am using only 10th pin. So only for B I am putting 1 0, so it will operate in non-inverting mode. Now this is just a summary. What has been explained already is just a summary. Now moving on, we have a table like this. So this is nothing new to us. If you have watched the video which was explained earlier, you would have known. If you have not watched, I will explain it here in a short way. So this is your discrete sawtooth waveform. Though I'm drawing it on a continuous line, please assume that it is discrete. It is something like this, right? So here OCR1A stores the period value. So whatever value up to which it should count is stored in OCR1A. What does it do? What is its function? That is the one which decides the sawtooth frequency. This value, up to what value you are counting, decides what will be the width here, time period of this sawtooth. Obviously, time period is nothing but a direct relation of, or direct reflection of frequency. And how do we update it? Do you operate your converter at a fixed frequency or at a variable frequency? We are assuming a fixed frequency DC-DC converter. So if I'm instructing it to produce sawtooth frequency at sawtooth with a frequency of 20 kilohertz, it should forever produce a sawtooth with 20 kilohertz. It should forever produce. So I will declare it once. So I will initialize it once in my void setup function, and from there on it will keep producing the sawtooth infinitely as long as power supply is available to the Arduino. So how often does it get updated? It gets updated only once in the void setup. Now its range can vary between all zeros, that is from 16 zeros to 16 ones. So it can vary from 0 to 65535. That is, it has 2 power 16 states. It can count up to 2 power 16 minus 1 because 0 is also included. Now what value I am intending to store here? I am intending to store a value of 799. Why? Why? Because my Arduino clock is of 16 megahertz. If my Arduino clock is 16 megahertz, it has a corresponding time period of 62.5 nanoseconds. I want 20 kilohertz switching frequency, which has a corresponding, sawtooth frequency is my switching frequency, which has a corresponding time period of 50 microseconds. Now, how many such 62.5 nanoseconds should be placed to obtain my 50 microsecond? That's the question. This is 62.5 nanosecond. How many such 62.5 nanoseconds must be placed to count such that this period reaches 50 microsecond? This is the question now. Let me draw this clearly. how many such 62.5 nanoseconds should be present so that which each clock pulse, each count happens per clock pulse. For each clock pulse it goes. But how many such, I know one with the 62.5 nanoseconds. So how many such 62.5 nanoseconds should be placed so that I can obtain 50 microsecond here. So it's a sawtooth waveform, it's a triangle, it's y is equal to mx line. So how many should I place? I should just divide 50 microsecond, this total time divided by the time of the clock, 62.5 nanosecond. If you do this, you will get 800. Since 0 is also included, I should count up to 799 so that there are totally 800 states. So that's why I'm counting up to 799 here. Now, coming to OCR1B register. This is going to decide my duty ratio. So if this is my duty ratio, let me draw it in another color. So if this is my duty ratio, this compare register, that is OCR1B, the value of the duty ratio will be stored in this register. So we update it at every iteration of the infinite loop. In our Arduino program, there is going to be a void loop section in which we will be updating this value at every iteration. We take a sample, compute the duty ratio, put the duty ratio value into this register. Again, we take another sample of the output voltage, compute the duty ratio, put that value of duty ratio into this register, and we keep doing that forever. So that's how this thing happens. Going on, moving on further, what would be the range of this? Duty ratio can vary between 0 and 1 only. It can vary only between 0 and 1. Here your 0 is all 0. Here your 1 is 800, right? So if I'm saying my 1 is 800, what I mean basically, whenever it comes to my digital system, 0 and 1 is no more a talk. It's always between two integral numbers because each bit stores a value and all you get are whole numbers basically. So when I say I'm scaling up my 0 to 1 to 0 to 800, I mean to say if this is 800, if this OCR1B is having a value of 800, then this will be my OCR1B. Here my OCR1B will be present. So it can have a value, not though its size is 16-bit, it cannot have a value of 2 power 16. Maximum it can have a value of only 800. Only that makes it meaningful. So that's the value, that's the maximum value which it can store. So yeah, what is the value which should be stored here? You compute a duty ratio, scale it to 800 and then store that value. So once this is done, you will get your duty ratio ready. If you are not very much sure of why we should multiply by this, I have put a video earlier, you can refer to that video. Now, if I am operating an open loop system, usually when you are working on a DC-DC converter, you just test whether the converter is working fine in open loop and then you go for closed loop. So when I want to test my converter in open loop, I will make sure that my duty ratio has a fixed value. So what will I do? I will write these codes. I will make sure that if I wish to have a duty ratio of 50%, this OCR1A will determine up to what value the sawtooth should count. This OCR1B will determine the duty ratio. So I will simply put 0.5 times of 800 here. So the moment it reaches 399, the PWM will go off. So this is a perfect 50% on period PWM. This is how you get. This is the syntax for Arduino code. You can just have a look at it. And these statements mean that in this register, I am writing 1 only to this register. I'm writing 1 only to this register. I'm writing 1 only to this register. So you can go to the register reference as I've already told, and then you can see where to write 1 and then you can write it. So what are we doing here in the void setup? This is for serial communication. You can just ignore it for now. And then the pin mode, since I want PWM out of pin 10, I am declaring it as output pin. I'm clearing all interrupts. I'm doing some manipulation, then I'm setting all interrupts. CLI stands for clear interrupts and SEI stands for set interrupt. So I'm clearing my interrupts. First, I'm writing all the registers to 0, and then I am writing values to OCR1A and OCR1B. This is the period register, this is the compare register. Since I have already initiated this to 0, now by default all the bits will be 0. Whichever bit I want to set to 1, I am setting only those bits to 1 using this command. This is for open loop. Now it has a fixed duty ratio. This is your duty ratio register. It's fixed. If I want a closed loop system, I will not put my OCR1B here. I will put that inside my void loop. So this segment will produce only sawtooth. It will keep producing a sawtooth of 20 kilohertz or 50 microsecond width forever. It will keep producing the sawtooth forever. And I will have another section called as void loop below this, under which I will do something, compute my duty ratio and store that value in OCR1B and close this. So this void loop keeps running in again and again, and my OCR1B register, which is the duty ratio register, will get updated every time this loop runs. So only my duty ratio will change slightly up or slightly down. My sawtooth will remain fixed. So with this we can conclude the discussion of configuring your timers.